Next up on stage is Professor Francesco Stellacci. Francesco has been with us since 2010 in material science, and his lab focuses on the creation, characterization, and functionalization of supramolecular interfaces that are present in the nanoscale and that are responsible for most of the materials functioning, thereby covering a wide range of topics from antiviral surfaces to recycling. Francesco, the stage is yours.
Thank you. Today I'm going to talk about and focus about the part of research in my lab that is about recycling. And the thing that I really would like to convey to everybody is the size of a problem we have in general in material, doing it through the example of plastics. We produce 50 kilograms of plastic per year per person. Each one of us is responsible, on average, in 2 years of our own life to produce more plastic than we actually weigh. And when this plastic is produced, where does it end up? Well, only 9% ends up being recycled, and the rest, it's 1/3 more or less incinerated, and that's a best case scenario when we produce CO2. Another third is just thrown in the environment, ends up in the ocean, and is generating islands in the oceans. There are two major islands, the North and South Grand Garbage Patch, that are the size of France and the Philippines, respectively, in the ocean, and they're growing. The other third is actually converted into microplastic. With that, it enters the environment, it enters the food chain, and we eat it. There's an estimate that we eat 5 milligrams of microplastic every week. And why do we generate microplastic? It's because, for example, when we move with a car, because of a friction of the tires that needs to be there for the car to move, we wear the tire and we consume it into microplastic that end up in the ocean. And it's not just the tire, it's the sole of our shoes. Look at your shoes. If the sole doesn't look perfect, you left microplastic in the environment. Now, are there solutions to this problem? Well, not really. We think that recycling is the solution to everything, but we forget that 9% of plastic is recycled, even though 75% is recyclable. And the difference is because virgin plastic is way too cheap. Entire countries don't have recycling facilities because it's too expensive. And the solution that in research we're looking at, for example, recycling back to monomers and producing against polymers, don't solve this problem. There is a credo that says that we should go for biosourced, biodegradable plastic. Biosourced means competing with food production, and so it has a cost. And biodegradable, if all plastic today were to be replaced by one biodegradable plastic, we would fill completely the environment with a single food for a single species that would change completely the ecosystem. So the problem is not so simple to solve. And so it's normal for a material scientist to ask, how does nature solve it? And why is this question plausible? The reason is plastics are material made of something that we call polymers. And natural polymers are the most abundant natural material because natural polymers are called proteins and DNA. How does nature recycle these materials? It does so avoiding accumulation. Let's take the example of a leaf. A leaf grows in one season, it's in use in one season, and degrades in one season. Well, we have needs for materials that last only 1 day, 2 days, a week. How can we do that? Or, if you want, how is a butterfly sustainable? My answer is that nature recycles proteins by their metabolism. So nature recycles plastic by their metabolism. Today you ate, you had a lunch, you ate a random mixture of proteins. Your body is right now chopping these proteins into their units. They are called amino acids. And then these amino acids end up in the cell, and in the cell, the ribosomes take information from the DNA and creates the protein you need at that moment. This is the best recycling example on earth, because you start with a random mixture, you don't separate it, and you produce every time a different thing, you produce every time what you need. Can this be the way we recycle the materials of the future? In my lab, we are trying to answer this question, hopefully positively. What we have done is we can take protein-based materials. What you see on the slide there is beta-lactoglobulin. It's a protein that is a side product of cheese production that my colleague Raffaele Mezzanga in ETH uses to produce water filtration apparatus that are in testing in poor countries in the world. Well, after they have reached their end of life, we digest them and we transform them in green fluorescent protein, a biomolecule that has a large market and a much higher value than the starting material. We can do that with silk. First, Omenetto at Tufts uses silk to produce electronic devices. Then we transform them in biomaterials. We would like to do this for packaging, and we would like to do this for many other applications. And in my lab, we are also working to do this with real synthetic polymers, starting from a mixture and recycling it. That's my dream. My dream is that next time I talk to you, the sole of my shoes will be made of proteins. Thank you.